Welcome to The Explainer. Today, we're going to crack the code on statistics. We're going to see how it's possible to make incredibly smart guesses about millions of people just by looking at a tiny, tiny fraction of them. So let's kick things off with a mystery that, when you think about it, is kind of mind-bending. It affects everything from who you think is going to win an election to whether a new drug is safe. How is it even possible? Well, it might seem like magic, but it's really just the power of a very clever, logical system. And this really gets to the very heart of the problem that statistics was invented to solve. See, we're super curious about the world, but we just can't see all of it at once. Okay, let's break this down. On one side, you've got the population. That's the whole shebang. The entire group you dream of knowing about, say every single citizen in a country called Statsland. It's just way too big to measure completely. So what do? We grab a sample. A small, manageable piece of that population that we can actually study. The entire game of statistics is figuring out how to use this small sample to say something smart and reliable about the whole population. So you've gone out and you've collected your sample data. What can you actually do with it? Well, there are basically two main moves in the statistician's playbook. First up is descriptive statistics. And you know what? The name says it all. You're simply describing what you see in your sample. So if we measure 4 students and find out their average height is 175.75 centimeters, well, that's just a fact about our little group. It's a neat, tidy summary of the data we actually have in our hands. And this is so important to get, that number only describes our little group of 4. To then turn around and claim that's the average height for all students everywhere? No way. That would be a huge leap, and we just can't justify it. Our description is stuck with our sample. So how do we make that leap? How do we go from our small group to the big one? Well, that's where the real power move comes in. We need inferential statistics. This is the amazing toolkit that lets us build a bridge from the data we have to the truth we're searching for in the whole population. Okay, so let's dive into this. How on earth can we make a reliable guess about the whole population when every single sample we take is going to be a little bit different? This seems like a deal breaker, but it's actually the key to everything. I mean, think about it, right? If we went out and picked a different 4 students, we'd get a slightly different average height. Of course we would. This natural little bit of variation from one sample to the next has a name, sampling error. And that name is a little tricky, because it's not an error, like a mistake. It's just the reality of only ever seeing a piece of the puzzle. So this is the million-dollar question, isn't it? If every sample gives me a slightly different answer, how can I ever trust the one answer from my one sample? How can it tell me anything real about the population's true average? The answer is one of the most powerful and honestly just beautiful ideas in all of math. It's called the central limit theorem. Just imagine this for a second. What if we didn't just take one sample? What if we took thousands of them? For each one, we'd calculate the average. And if we took all those thousands of different averages and plotted them on a graph, something absolutely incredible would emerge from all that randomness. That pattern is a perfect, symmetrical bell curve. The theorem basically guarantees that as long as your sample is big enough, and big enough is often just around 30, the averages you collect will always organize themselves into this predictable shape. And here's the truly wild part. This works even if the original population is shaped all weird and lopsided. The averages of its samples will still form that perfect bell. This is the secret weapon, because a predictable pattern means we can start calculating odds. Okay, that's a cool math trick, but how does this bell curve help us in the real world with our one sample? Well, it's everything. It lets us move from making a single, lonely guess to making a confident statement about where the true answer is probably hiding. Let's make this real. Say we do a survey, and our one sample gives us an average income of $52,100. This is what we call our point estimate. It's our single best guess. But we have to be honest, right? We know about sampling error. What are the chances that our one number is the exact, down-to-the-penny, true average income for the entire country? Pretty much 0. It's probably close, but it's almost certainly not perfect. So instead of offering up this one number that we know is probably a little bit off, we do something much smarter. We build a confidence interval. We take our best guess, the point estimate, and we add and subtract a little buffer zone. That buffer is called the margin of error. This gives us a range, and now we can say something like, We are 95% confident that the true population average is somewhere in this range. See, it's an educated guess that's honest about its own uncertainty. And what's great is that this gives us control. You want a more precise estimate? You want to shrink that margin of error? The best way is to increase your sample size. The more data you collect, the tighter and skinnier that bell curve gets, and the smaller your margin of error becomes. It's a direct trade-off. More work gets you more precision. All right, we are on the home stretch. Let's put all these pieces together for the grand finale, using our sample data as evidence to put a specific claim on trial. This whole process is called hypothesis testing, and you can totally think of it like a courtroom drama. You've got two competing claims. The null hypothesis, we call it H0, is the status quo, the default assumption. It's the innocent until proven guilty position. Then you've got the alternative hypothesis, or H1. This is the challenger, the new claim that's trying to prove the status quo is wrong. Now, just like in a real courtroom, the jury can make a mistake. In statistics, a type 1 error is a false alarm. It's like convicting an innocent person. We reject the null hypothesis when it was actually true. A type 2 error is a missed clue. It's when we let a guilty person walk free. We failed to reject the null hypothesis when it was actually false. And statisticians are always trying to balance the risk of making these two kinds of errors. And this brings us to the most important rule of this whole statistical courtroom, the verdict. We never say we accept the null hypothesis. We never prove it's true. We can only do one of two things. Either we find enough evidence in our sample to reject the null hypothesis, or we fail to reject it. It's a subtle difference, but it's everything. A lack of evidence to convict someone isn't the same thing as proof of their innocence. And that, right there, is the perfect way to think about statistics. It's not a machine that spits out absolute proof. It's a method for gathering evidence, weighing it carefully, and making the most informed decision you can in a world that is full of uncertainty. So, there you have it, the full journey, from a single sample to a confident range of possibilities, all the way to a formal verdict on a claim. It's this powerful toolkit that lets us navigate a complicated world, which leaves us with just one final question. Now that you know how the tools work, what big claim would you want to put to the test?